In the interest of staying on schedule, our first speaker of the afternoon is Peter Constantine, and his topic is weak solutions. And you have 50 minutes.
Thank you very much. What?
50 minutes and then questions.
Sure. Thank you very much. So, as I said earlier this morning, it's a pleasure to be here. Thank you for the invitation. I truly enjoy the Institute and Cambridge. So I'm going to talk about weak solutions of hydrodynamic equations and some regularity results. And then I'm going to talk about the Onsager conjecture, and which is related to weak solutions of Euler equations. And at that point, I'm going to talk also about some local interactions in Euler equations. So there are two topics here. There is the topic on quasi-geostrophic equations. It will be clear in a second. And that's work with Jiahong Wu, who is at Oklahoma State, and Gautam Iyer at Stanford. And the work on Onsager conjecture is with Alexei Cheskidov in Chicago, Susan Friedlander, which now is USC, and Roman Shvitkoy also at UIC. So I'm going to talk about the quasi-geostrophic equations for a little moment. So I'll remind you, these are the Euler equations that we all know, and they have various criteria for regularity, and I write here the famous Biel-Kato-Maida result that the time integral of the magnitude of maximum magnitude of vorticity should be finite in order to get regularity. The equations I'm going to talk about are simpler, but they have some physical motivation. They appear as a simplified version of the full quasi-geostrophic equations. They are the surface quasi-geostrophic equations. And they have, although they have physical motivation, the reason why they have been studied for like 13 years or so or more, they are some sort of a laboratory for studying Euler and Navier-Stokes equations. So here is the equation. The advantages are that there is one scalar as opposed to a vector. So I'm advecting a scalar. It's an active scalar because the velocity is computed from the scalar by some time-independent law. And there is possibly a dissipative term. So this dissipation is a power of the Laplacian. And the power of the Laplacian is here, it's S over 2. So in Fourier space, you can think of penalizing or damping with wave number dependent damping, and the modulus, or if you are a wave number k, the damping is wave number k to the power s. So this number s will be positive, and however, we can discuss both kappa equals 0 and not 0. So that would be the inviscid one, and the dimension is 2. So the advantages here, you can do it in n dimensions. The advantages over the full hydrodynamic equations are scalar, and n equals 2 is already interesting. Instead of vortex lines, you have level sets of theta, and they obey a vorticity equation. If you take the tangent vector, so this is the rotated gradient. The gradient is normal to the iso level set. The rotated gradient, you're in 2 dimensions. You know what you mean by rotation, pi over 2. And then that's a tangent vector to the iso level set. And it obeys exactly, if kappa is 0, the same equation as the equation that was written here in the arrays, the equation of transport of the tangent field. So it is transports the level sets are material. And they have same Biel-Kato-Maida criterion. They have lots of other similarities with the Navier-Stokes and Euler. So, and the main thing is that the problems are still open. So I'm talking about weak solutions for nonlinear PDE. So first of all, I would like to emphasize to some of the people who are mainly numerical people, why should you care about weak solutions? You can think of them as what happens to your numerics when you remove the various whistles and bells that you put in order to get them to actually fit on the computer. Truncations, the finite dimensionality that's intrinsic in numerical analysis is an approximation of the solution. Weak solutions are obtained by removing those and maintaining limited information about the solution, not strong enough to differentiate at every moment. So what are weak solutions of nonlinear PDE? There is no such thing in general. There is no recipe to obtain such things. So a typical methodology is you take a good approximation, you integrate by parts, remove the derivatives on test functions, and if you are lucky, you have a weak continuity. So allows you for the nonlinearity to somehow pass to the limit. So a typical example for the Euler equations, and this is a partial definition, if the, the space here has to be intersected with divergence free, it's not written, but what's written here takes advantage of divergence free, and then you have a balance that you write your solution, you dot it into some unknown test function, and then you get a balance that comes from the equation by integration by parts. That's the definition, and ignore the spaces for a little while. I'll insist on spaces when it's necessary. For the quasi-geostrophic, there is a similar expression. The places where you put the solution, these are spaces of functions that essentially come to you for free from the structure of the equation. The equation has some energy that's conserved usually. So it comes from good structure derived from Lagrangian or something, and then it has automatic energies, and those are encoded here in fancy language in the spaces that are the spaces in which the solution lives for free, for without any work. So these are the concepts. So in some sense, if you wish, weak solutions are not, because I had physicist friends who were telling me, thinking weak solution is a function that solves the equation almost everywhere. I heard that. No, they're not solutions that solve the equation almost everywhere. That's not a weak solution. You would completely miss ranking Hugoniot condition on shock equations if you would say only solves almost everywhere. So there are solutions that solve the equation in a very large space where you allow to interpret the derivative by integration by parts in a weak sense. So you would like locally square integrable evolutionary weak solutions obtained as limits of good approximate solutions U epsilon. The reason for this statement is that there are ways of constructing weak solutions that are extremely weak and extremely pathological, but they are not like this. And those can mislead you in thinking that very bizarre things can happen, but they will never happen in a numerical computation because they lack this kind of a structure. Oh, absolutely. So there are solutions of the Euler equation, weak solutions of Euler equations that are not continuous in time. They're not continuous, not functions of time. They're distributions. They're constructed. For instance, there exist examples now of weak solutions of Euler equations with compact support in space-time. Okay? But there are weak solutions that are not of this type. They are not evolutionary weak solutions. And they're not, so they're interesting, but not the thing that I'm talking about. So what you need is some sort of a weak continuity, meaning that the fluxes, the nonlinearity, at least if I take the approximation away, should converge to the nonlinearity. Okay, so that's a requirement, and those don't have that kind of requirement. This is a strong requirement because you take limits of quadratic quantities, and those usually don't converge. If you know that the linear quantities converge, it doesn't follow that the quadratic quantities converge. And there are simple examples, as you very well know, how you generate concentrations, for instance. All right. So weak solutions are known for the quasi-geostrophic equation without viscosity, without damping. They are not known for 3D Euler. Okay? So the reason I'm going to actually show you why they are known for QG. and the reason is structural, not dimensional. Okay, so let me show you the QG. Very simple calculation, and it explains what's going on. So for the QG, we can write, this is QG without dissipation. Just transport, and remember that U is computed from theta. So in Fourier space, if you, this is your theta, U is simply dividing by theta hat of J divided by modulus J is U, right? Sorry, I have a J perp divided by modulus J, that's U, okay? So for instance, here you see U at J dotted into grad theta, okay, at K.
So U is at least free divergent?
Yes, automatically because of this J perp, okay? Right, so U is simply in Fourier space is theta hat times J perp, okay? And an I there to make it
I'm
real.
sorry, I missed what the operator R part was.
So this is exactly that. So let me write it here. So I have R perp of theta. Now I have to, is U. Let's Fourier transform this to understand what I said. R perp of theta Fourier at some wave number K is square root of -1 for aesthetic reasons, so that I get a real function. K perp over the length of K times theta hat of K. So R is the Riesz transform is d1, d2 minus Laplacian minus a hat. So this is order 0. Okay, and R perp is minus R2, R1. Okay.
What is the one?
Huh? What?
Is why D1 and D2?
2 dimensions. We're in 2 dimensions.
No, I thought we were.
We can do something in 3D, but this is just interesting, simple, okay? 2 dimensions. As I said, there isn't, the problem is open. For instance, for this problem, blow up for this thing is open. It's not known, okay? So here is why I have weak solutions for these equations in L2. This conserves L2 automatically for free and has nice properties. Here is how it looks as an infinite system of ODEs, okay? So here is the Fourier coefficient. I'm sitting at wave number L, and I sum all the contributions from J plus K equals L. These are vectors in Z2, periodic. And this is the interaction. Okay, this is U dot grad theta. Okay? And 2 i's make me a -1, and there is another -1. In the end, you'll believe me, there is no more i's, but doesn't matter. Now you use the antisymmetry. You see this is symmetric in J and K. This is antisymmetric in J and K. This is symmetric in J and K. So obviously, in order for this to be non-zero, you need to put here an antisymmetric piece to keep it antisymmetric. Otherwise, it vanishes. So what I said is you write this as sum, half the sum and half the difference, but only half the difference survives. And then you look at this expression, and now you have another way of writing the same thing, in which you have a coefficient here, and the coefficient is J perp K, 1 over J minus 1 over K, and so on. That's all. You stare at it for a second, use triangle inequality, you notice that you sit at wave number L. If you are willing to pay a price of L square, you pick up downstairs J and K, both of them, or rather the maximum between them. Okay, that's just triangle inequality. And consequently, the same thing is written here in a fancier way. You take the nonlinearity, which is U dot grad theta, at some theta and at some other theta, divide by the Laplacian, divide by this, and measure it in some weak norm. I'll tell you in a second, it's written here what the weak norm is. And you get that you can measure it by the increment in the same weak norm, actually almost like an Osgood, almost to power 1, right? You have really very nicely 1 plus log of something, times only L2 here. So this is almost a continuity, right? In the weak norm. Actually, it's almost Lipschitz continuity in the weak norm. The weak norm is simply the supremum of the Fourier transform. So the supremum of the Fourier coefficients is extremely weak norm on the function. I'm not summing, I'm not assuming any decay. These are actually for measures. It doesn't tell you more than the function is a measure. But you measure the difference between two solutions in terms of the difference between two solutions. Nonlinearity in terms of the linear piece. And the price you pay is this, only L2, but this is conserved on solutions. So this statement means, this is quasi-Lipschitz, like an Osgood Lipschitz. You lose derivatives because here I'm dividing by Laplacian and comparing with undivided. So, but for weak solutions that doesn't matter because a weak solution is what? Is something that I test it with a test function. So I can integrate by parts and throw all the derivatives on the test function. If I want to measure the scalar product between my function and phi, I can put a Laplacian and divide by a Laplacian. So I can measure it by dividing by a Laplacian. So the loss of derivatives does not impede existence, but prevents uniqueness. I would have uniqueness of weak solutions if this would not be here. Okay? Now I'm going to talk a little bit about regularity. So regularity and uniqueness with critical dissipation. So I have to remind you a little bit about the equation. If I have dissipation, here it is. Oops. This is the equation. This is like one derivative, okay? 1k. So if S is larger than 1, just counting, here I have more derivatives than I have here, okay? And if S is 1, it's called critical. The reason for it is simple, that if you have a very small parameter here and your initial data are large, this is quadratic. It looks like theta squared divided by 1 gradient. This looks like a little bit times divided by 1 gradient. I don't have anything to play with, so in principle, danger could occur, and singularities might occur. So we'll go to that in a second. But let me say...
What is gamma again? Go back to it's something in the nonlinear.
That's just a connection coefficient, right? The gamma is this guy, right?
Oh, it's the connection coefficient.
It's really the
before I
coefficient.
know.
Why is it not theta squared, right?
Right.
So you have a thing like this in Euler also if you write it in Fourier.
Right.
So for the dissipated one, in the critical case, so supercritical when S is larger than 1 is easy, and things are very nice. We proved existence for small data in L infinity, which is a nice result, but now we have global existence for large data for all initial data at S equals 1. If you take Burger's, you can do the same game. You take Burger's equation and put here a dissipation, a fractional dissipation, and ask yourself what happens. Then Kiselev, Nazarov, and Sternberg proved that when S is less than 1, this thing blows up for Burger's. Okay? For S equals 1, it's regular. And for supercritical dissipation, I expect this quasi-geostrophic guy, not Burger's, not to blow up. So mainly the main point here is that the inviscid equation dominates the behavior. If you have Burger's in the inviscid equation, which you know blows up, supercritical, meaning S less than 1 here, cannot save you. And on the other hand, if, as I expect, this thing will be irregular, like Euler, it will be irregular in the inviscid limit, then a way to get to that is try to study what happens when S is less than 1 and try to get regularity there. So I'm going to explain a little bit this statement here, that there is a gap from passing from no gap from L infinity to C delta, but there is the gap passing from L infinity to C delta, but there is a gap, no gap from L2 to L infinity, and so forth. So here are some results, okay, about the supercritical case. So it's open, okay. The problem with supercritical dissipation or the problem with no dissipation at all are open, okay, for 2D quasi-geostrophic. Nobody knows. So the first result is that if I have initial data that are just square integrable, then the solution is bounded, okay. So that's not hard to do. And the velocity is BMO, but this follows from the fact, trivially, from the fact that the solution is bounded. So not only it's bounded, but it has a natural decay in time. Okay? So that's one result, and this is for, again, for Lorey-Hopf weak solutions, meaning solutions that obey the energy inequality, and arbitrary supercritical S. How am I for time? Let's see. I have to make choices. What
Half an hour.
Half an hour. All right. So I will tell you something about the proof, but only kind of like impressionistically. So the idea, the whole idea, we're going to use a strategy that comes from Di Giorgi. It's a great mathematician, and it was used a lot by Caffarelli, and then it was used by Caffarelli and Vasseur for precisely these equations in the critical case. So the idea is that these are scalar equations with kind of like imaginary Laplacian. They are, if you change variables, if you take a function, a convex function of the scalar, that dissipates also, you know, because the Laplacian, if it was a Laplacian, the Laplacian of a phi of v is nice and has a nice sign. So that's the general idea. Now these are not local. I don't have Laplacian of a v. I have a very non-local operator, so I have to be very clever about that. But it turns out that there is a way to do it. So then what you do is you take the energy, which is God-given in this case, and then you essentially rescale. You decide to cut off the function. This is a convex function almost. So it is, you take the function, you cut it above something and put it to be that constant. Well, it has a little nastiness there, but that's a convex function. So you can modify that to make it into a nice function. And then you do energy on this function of theta. You get the energy, then you rescale this in a horrible fashion. When you rescale it and choose things right, you get by moving this up, you get an inequality that the higher one is a high power than 1 of the previous one, and that proves that if you start below 1, this will tend exponentially to 0. So that essentially tells you that at some point, if this is high enough, you don't have anybody living higher than that. It's 0. So that is a bound in L infinity.
So you have this energy which involves the hyperviscous term?
It's hypo.
Hypo.
Hypo-viscous, right?
So
So this is just the energy. If you didn't have this thing here, this is just the energy that you would get automatically by dotting the equation into theta, multiplying by theta and integrating by parts.
Okay.
Here you are saying, I'm going to take theta and cut it above a certain height, right? So I take the positive part of theta minus some constant. The constant is m. And I'm going to play around by taking m minus something and move towards m. And I'm going to have this m to be large enough. If that is large enough, then I can prove that actually this thing is going to be 0. All right? So in other words, there is no piece above m, therefore theta is less than m. That's how it works.
As you imagine your plus, does it make it into compact support?
Well, no, you don't use that. But no, it could. It could. So if the thing would have been, you don't use that. You simply are using the fact that the function that I'm using, if you think of it, is I take a function that's identity up to a point, right? So I'm taking the function x and then blah, right? So it's nice convex, right? And therefore, think of it as being the way I change my variables. I take in front of the function theta, I take that convex change of variables, and it will still obey an energy inequality. That's all you're using. And then you are relating how you march up, you crank up this guy, and you relate the next level to the previous level, and lo and behold, you have something that evolves super linearly, and therefore if it starts less than 1, it goes exponentially to 0. That's the whole thing. It's Di Giorgi invented this for elliptic equations. Okay, this next theorem tells you how to go from L infinity, which we just got, to C delta, Hölder continuous a little bit. Well, here is, and I'm going to mention only a little bit. Here you need to assume that what you are advecting with is Hölder a little bit. How much? The defect between your dissipation and 1. So let me restate this again. Imagine the case s equals 1. Then this is no assumption, almost. So imagine that theta in L infinity implies u in L infinity. It doesn't. It implies BMO, but it's, let's say, close to being correct. Then if s is 1, what I'm saying here is that Caffarelli and Vasseur were lucky, because this theorem for s less than 1 requires an assumption, but for s equals 1 does not. Okay? So you get from L infinity to C delta if you assume something. So this is what I meant by having a gap, passing from L infinity to C delta with this technology. So this is a highly technical proof. Because it requires, first of all, a very brilliant idea that Caffarelli and Vasseur had in the s equals 1 case to add one more dimension and replace the non-local lambda, which is a non-local operator, with the Dirichlet to Neumann map for the harmonic function extended. So you know that it's solved by the Poisson kernel, and that gives you a Dirichlet to Neumann map. So the inverse of that is a Poisson kernel. So that's, you can do even for fractional Laplacian, and that's called a Caffarelli-Silvestre harmonic extension. Silvestre is now at the University of Chicago. And then you have isoperimetric inequality of Di Giorgi, and you have a diminishing oscillation lemma. I'll state only, so here is the extension. I'll give you an example. If I take a harmonic, think of this S again to be 1 for simplicity first. If S is 1, B is 0, and here I have the Laplace's equation. I'm extending the function theta in the upper half plane or upper three-dimensional thing, z positive, by saying I'm going to have a harmonic function whose boundary values are theta. And then lambda to the power 1 is the normal derivative of that guy. So Dirichlet to Neumann map. This is still true for fractional Laplacian. So if I poke of an S here that's not 1, then I have to put here a fractional power, which is the defect to 1. And still true. So although this is not harmonic, it's good enough elliptic operator. And therefore, this is a Caffarelli-Silvestre extension. And diminishing oscillation means the following. You take a solution. Now, a cube of radius 4 in this extended variable has a star. You assume it's bounded by 2, and you deduce that there is a lambda star depending on S, actually, and on the norm of U, which is not here, so that the oscillation is strictly less than 4 in a smaller ball. Okay? Again, very elliptic kind of argument. Really hard to get, but once you have this, essentially the rest is scaling, and you can obtain the existence of the passing to C delta. Now, passing from C delta to C infinity is done using the next tool, and I'm getting into my next topic. So passing from C delta, if I know already that I am in what delta is sufficiently good and the function theta is in C delta, then the function is in C infinity, and this is done with Littlewood-Paley energy estimates. Now I'm going to belabor the proof. I'm going to state another theorem without, so you see here that we have for the supercritical, these three theorems don't add up together to a theorem of regularity. I can go from L2 to L infinity. I go from L infinity to C delta, but I need to know something I don't know. And where I got there, I had to get there with a delta that's large enough that I don't know that I did there, and then I'm home. So there are two gaps, okay? In
two gaps, you went L2 to L infinity.
L2 to L infinity is fine. L infinity to C delta, there is a gap. I need U to be good.
Okay.
And then from C delta to C infinity, I need delta to be good.
Oh, your objective is C infinity.
Yeah, I need regularity.
Yeah, correct.
So this, however, if you modify the equations so that they look critical, so this you keep at S, but you have actually better velocity, so that the number of derivatives in both expressions is S. Here is S derivatives. Here is one derivative. Here is minus one derivative. Here is S. So together it's again S. If you are in that case, oops, then you have C infinity. So there are no more gaps because you are in some sense still back to critical. So this requires essentially all the stuff before and a little more in the Littlewood Paley. So now, how much time do I have?
20 minutes.
Okay. So this was about the regularity. The rest of the talk will be about Euler equations and the Onsager equation, but I needed to get to the Littlewood Paley, so I want to use a little bit, a few seconds to remind you what the Littlewood Paley decomposition is. It's essentially windows that are dyadic. You decompose your function. Notice that my decomposition here is going to go from j equals -1 to infinity naught. Customary is go all the way to j to minus infinity here, but that goes to very large scales, and we're not interested. We're dealing with things that decay. And this delta j of u is like this. It's an operator, it's a window. In Fourier transform, the support of it is about 2j, 2 to the power j. So you are stopping at 2 to the power j. They don't talk to each other if they're separated by more than 2, including 2 units. So 2 octaves down, the supports become disjoint. If you sit at 1 in the middle one, and they add up to the identity, but they already add up to the identity if you sum 3 of them if you sit at 1. Okay? So 3 guys, you sit in the middle, you put 3 windows, they add up on top.
Delta J is a Laplacian.
No. Delta J is Fourier transform. So delta J, you multiply the Fourier transform with a function phi j.
Phi J, okay.
Phi j looks like a window, but it's actually...
Oh, okay, that type of... Okay,
Right. So delta J is not a Laplacian.
okay.
But that's the notation, unfortunately. And if you sum all the guys, and you look what happens at J, so you have a product here of 2 functions, one summed all the way to almost k minus 2, and then you look at delta, there is a reason for that, and just bear with me, and you multiply with delta k, then this talks only, roughly speaking, back in the k. Okay? So this is, these are basic properties. So here is how it's constructed very briefly. So I'm used to writing pseudo-differential operators, but you think of it as being Fourier transform means the Fourier of this on Xi. Okay? So you take a function, think of it this way. I have the Fourier, the little psi, this is big psi, this is little psi. You multiply multiply the Fourier transform, I misspoke, this is the same. So you multiply the Fourier transform by psi, and then come back. Okay? And the psi is rescalings of the same template, psi 0. Okay? And this template, for j non-zero, this template has no support near 0. Okay? All right. Now we need to talk a little bit about spaces. But I insist at the end I'm going to give you a proof of the interaction, locality of interactions in Fourier space for Euler equations. So patience, there is a reward at the end. So we need to talk about spaces. And these are Christmas tree spaces with 3 indices. Okay, S is the number of derivatives. P is in what physical space integrate to power P. So L2 is integrate to square, L cube is integrate to cube. And this other parameter Q here is you take the sequence of delta J's. I have a sequence of functions. I can integrate them in space. I get a sequence of numbers. And then I can measure that sequence in some way. I can sum the squares, I can sum the cubes. And those are little LQs here. Okay? So summing to power 1 will be Q equals 1 and so forth.
So the subscript J's, is that going back to the Littlewood
Right.
Paley?
So this guy is delta J of u. I apologize for not stating that, but
and
maybe.
then you take a derivative of that and you do
The
another.
derivative costs exactly 2 to the j. S derivatives costs 2 to the sj.
Okay, and then you do it again. There's another subscript J. on that.
Right, you take the whole sequence and then you look at all this sequence. You can take, these are functions of x. You can integrate it to the power p, take the norm. You got yourself a sequence of numbers. You can say now, when I have the sequence of number, how am I going to measure that sequence of numbers? I can take the sum of the absolute values. I can take the sum squared. That's measured here. Okay? So in particular, I have another space that is coming. And if you put here the infinity, that means you take the maximum of these numbers. So for q equals infinity, you get the maximum. Like L infinity is the maximum. And a subspace of infinity is those for which, as j goes to infinity, you go to 0. Right? And that's in classical Banach spaces, it's called a little c. Right? It's a sequence, subsequences that converge to 0. Bounded, of course. Okay? So these are tools, but it's worth writing them for a second. This is dimensional analysis. It tells you that if I measure at frequency j in some high LB here, okay, I can measure a higher LP by a lower LP, which is something that's forbidden to you in general life, and you pay a price that's exactly the dimension that you think is lacking there, because this lives at wave number j, 2 to the j, and this therefore has a length scale 2 to the minus j, and if you put that length scale, this is the correction between LP and LB and LA. Dimensional analysis. You can go up, you cannot go down. And you have the Sobolev thing, in which says, if I want again to measure something at a higher derivative, I can measure a higher derivative, this is S, by a lower derivative by paying in B. Okay, and then the mismatch is, again, dimensionally correct. Another one that's important here is that I can, if I make in little L2 here, if A is larger than 2, if I measure in this piece larger or equal than 2, and I measure this Q is exactly 2, then I can measure the LP or LA norm. All right, those are very well known. So now I'm going to do the following two things. I'm going to state why we don't have weak solutions in Euler, what's missing, and because you saw what did work for quasi-geostrophic, and then the Onsager thing, and then I'll quit. So here is the nonlinearity for Euler. I'm doing it like bilinear. U dot grad V, project it on divergence free. Okay? So you can write this, and it's very useful. You pull out a derivative because these are divergence free. So here is a derivative, and then there is some non-local operator here, matrix, horrible thing. But it's like the Hilbert transform. It's a zero-order multiplier in Fourier space. Okay? So I have one derivative, something's non-local but doesn't differentiate, and then I have U tensor V, the matrix. Okay? So here it is, written in full glory with all Riesz transforms, where the Riesz transforms now are 3 of them, and they're exactly those guys. One derivative divided by half a Laplacian. Okay? And then, and lambda is lambda. Now, I take this little Paley at wave number q. So I take the nonlinearity and project it or window it at wave number q, something that everybody who does turbulence does in one way or another. And then again, something that everybody who does turbulence does, I decompose it into 2 pieces, and they have names because this was done by Bonny, and Bonny called it paradifferential calculus because he didn't want to have people understand what he's doing. These are commensurate and incommensurate. How about that? Okay, so you are at Q and you're looking, sum together the commensurate contributions from the U and V, and here incommensurate contributions. So the commensurate contributions are, so I'm projecting at Q, and I look at the nonlinearity, and I look only at P and P prime that are commensurate. Okay, P minus P prime of order 2. It turns out that you have to start beyond Q. So if Q is 1 million, these guys are really 1 million, or each one of them. Okay, that's good. That means you, in some sense, that if you are deep in, this thing doesn't visit the large scales. And the incommensurate turns out, the complement of this, turns out that are of the type that I wrote before. I have the sum up to Q for one guy, and the exactly Q component for the other guy, with a little blur, J minus 2 doesn't really matter. So think of them as being the sum up to Q times exactly Q, and vice versa, of course, because it's bilinear. Okay? So the main point is that I would like, in order to get L2 weak solutions for Euler, I would like to be allowed to punish the difference. It's always about differences because you're doing approximations. You want to show that the approximations converge to Euler. So I take one, I take another, I take the difference, and I want the differences to start going to 0 so I get my nonlinearity. So I take one nonlinearity, another nonlinearity, and I'm willing to pay here as much a price as possible because I'm going to throw it on the test function anyway. So I would like to have an inequality of the type that I am allowed to use a weak norm here and pay only L2, which is the conserved quantity for Euler, and get continuity. This is an exponent here. Any exponent that's non-zero would do it because it will give me some weak continuity. All right? And the answer is that this is true for one piece, for the incommensurate, and not true for the commensurate. We cannot do this for the commensurate because if I sit at Q, these guys run away deep in the ultraviolet spectrum. They run away, and I'm at Q, and I can divide by 2 to the Q as much as I wish. I never catch P. I never catch P prime. So let's think of it this way. Shell models and Gagliorkin approximations. This piece here looks like a shell model, not algebraically closed, but it says that I am dealing with nearby interactions at Q. These guys, however, it's kind of like a shell model that runs far. This looks like a leaky Gagliorkin, in which you say I sit at Q and I see up to Q, maybe leaking a little ahead, but not much. Okay? So the statement is that for weak solutions, the commensurate don't work, but the incommensurate work.
Work in what sense?
In the sense that this inequality is true.
Okay.
And for
The inequality from the last page. Right?
this one,
This
the desired one.
Okay.
You
Which
can do
part
this-
is incommensurate? Which part is commensurate and incommensurate?
C and I. So the commensurate, right? So I is the incommensurate guy, so which looks like a Gagliorkin.
Oh, I see. So you just have the incommensurate part down there.
So if I have the incommensurate part, it's good. This thing for incommensurate part is good, but it's not good for CUV. And for weak solutions in the next page, this is good and IUV is bad. So for existence of, let's put it this way, for smoother things is the other way around. These are only L2. Okay, so now finally the promised thing about the flux. So you are interested in the flux, and the flux, remember, this is the time derivative of the content of the Fourier content up to n. N of these Paley, Littlewood Paley guys. So you go up to some range, you take the projection there, and you take time derivative, and then you call that pi n. That's your flux. Okay, it's formal because I don't know, I have solutions that, what kind of solutions I'm talking about, but definitely for smooth solutions, this is not formal, it's exact. Okay? The Onsager conjecture says that if the solution of the Euler equation is smoother than Hölder with exponent 1/3, then the energy is conserved, and vice versa. That if the solution is less or equal to 1/3 regularity, then energy is not conserved. There are solutions that dissipate energy. Okay. There are results that go from left to right. So if I have a lot of smoothness, more than 1/3, then I conserve energy. So in this spirit, I give you the world record, okay, right now. So the world record is the following. You are assuming that the function in time is integral to the power 3. In space, it belongs to this best of space. So it has exactly 1/3 derivatives measured also in L3, raised to the power 3. And each, if you look at the Fourier or the Littlewood Paley components and you go deep in J, they go to 0. So the difference between this space and this space is that here, as you go deep in J, this goes to 0. Here, they're just bounded. So if you are in this space,
Going into J is essentially going into higher wave.
yes, high wave
higher
numbers.
shells.
High shells, right. So if you take, this statement here is the following. You take the shell J multiplied by 2 to the power J, that's a wave number, times 1/3, that's the number of derivatives. Measure that function in L3. Look what happens as J goes to infinity, you get 0. Okay, that's this space. This space is, look what happens as J equals infinity, you get just some bound. It's not infinity, but it's bound. So if there exist functions, divergence-free functions that are in this space for which the flux do not vanish, this would be consistent. This doesn't prove Onsager conjecture because these are not solutions of Euler. They're just kind of like the Lou-Doering thing. They're functions in function space. You measure at that instance of time the dissipation of kinetic energy, and it's not 0. The conservation of kinetic energy, and it's not conserved. Okay? But you don't know that that thing is sustainable in time.
Peter?
Yes, I'm okay. So there are also results for helicity of this type. Okay, so I'm not going to talk about that. And now finally, what I promised that I'm going to, in the proof, I'll give you a result about the locality of interactions in L2. So I'm going to not give you the proof maybe, but if you want I can show it to you. I'll tell you what is the statement. This is the locality kernel actually. To the left, you are going, because 2 to the j is power, you go like 4/3 negative, right? Because j is negative. Sorry, 2/3 to the left. And to the right, you go 4/3. Okay, and the statement is that if you measure the Fourier coefficient L cube in space with a corresponding thing, and you take the sequence of numbers, right? And for very negative guys, I put 0 because I'm periodic. I don't really care about, there is no such thing as very large scales. Then this proposition is what I promised. Then if you compute the flux at n, it is less than the convolution of your Fourier coefficients with k. So that means the peak is where you are, and below is going to be damped to the right to the higher wave numbers, like a 4/3 power, and to the left like 2/3 power, and you need only L2. This you have always. Navier-Stokes, Euler for everybody. Okay, so once you prove this, if you know, so the conclusion is that if you know that these guys will be going to 0, you get the flux is going to 0, so you have conservation of energy. And if you know only that they are bounded, well, then you know that the fluxes are bounded, but that's all. Okay, so it has to do with this quantity, which is essentially the Onsager quantity. It's a 1/3 derivative at the shell j, and how delicately do they decay as j goes to infinity? Do they decay or not? Okay, if they do decay, you have conservation. So in some sense, this is as good or as sharp as you can think, because in the same space in which they don't decay, you get examples where this doesn't go to 0. So I think that you don't want to see more of the proof, but if you do, and I have a minute or so, the idea is that you take the projection in the product, and then all the idea of ours with our Winan and Titi is that if you want to filter something, it's better to filter in each component than filter only one. And then the difference between this and the filter of both is a good object, and you can compute this object, and then the rest is, I'm not going to show you the details, but it's really very easy. If you want to see the proof, it's really very easy. So I'm going to stop and give you the outlook. So weak solutions in the correct spaces require special nonlinear structure. The linear structure is that you find a way to grab this beast that runs to infinity in wave number and punish it here, and somehow the whip here is felt all the way there. Okay? And that happens in quasi-geostrophic and doesn't seem to be happening in oil. The supercritical QG problem is open. In particular, no dissipation is like an Euler problem. It can be computed. Everybody computed to times 7. Same initial data. They all overlap beautifully. And after that, nobody computed. And I keep saying people should compute beyond that. It's a very doable problem, I guess. Anyway. So, and then the anomalous dissipation of energy, we are close to optimal spaces. And by that I mean, in order to actually prove the Onsager conjecture, you need to produce solutions of weak solutions of Euler in exactly B133 infinity, and we don't know how to do that because of one of those interactions. So thank you very much.
Questions? So it's basically this extra nonlinearity that's different in full 3D Euler, the way you express it in the Bessoff space, that you cannot sort of contain it in the way you can with the quasi-geostrophic. Is that sort of what your conclusion is?
That's essentially the kicker, right? So that's what makes the difference for weak solutions, for the ability to talk about long-lived solutions for Euler equations, for the ability to talk about the kind of solutions that dissipate energy. We want to understand what are the possible inviscid limits that perhaps have a positive epsilon. Those will have to be, if you don't put boundaries, if you put like everybody computes in periodic or something, then those will have to be solutions of Euler. And there would have to be weak solutions of Euler of a certain type. And the question is, what kind of solutions are those? And do they exist in some reasonable sense? Okay, so that's essentially where we are.
Okay. Any other questions? Yeah.
So I was interested by your comment that numerical people should try to look at these solutions, at these weak solutions. So what do you propose, more or less, so we can have an idea? Because when you have numerical method, you typically have some continuous function. So how close would they be, maybe in a finite singular, in a nearly singular behavior? How close will our numerical solution get to the weak solutions?
So you see, some of these things that we need, right? So the question about having weak solutions has to do with things of this sort. So you take the nonlinearity that you compute, and perhaps you try to study a convergence or a stability. You have two solutions and you compare the two solutions, compare the nonlinearities. And usually when people do these things, they do them indeed in very weak norms, like it's here. And not this weak, these are really extremely weak, but L2, they take energy difference, okay? And you want essentially to make sure that you have some kind of a continuity in the same norm. Here is a Hölder continuity, the norm W. But the constant that you pay is a constant that's conserved under the inviscid evolution. So that this is guaranteed by all means to be completely bounded in your approximation. And you know it's going to be bounded in the solution that you get. Okay? So that's why it's in Euler, you need a positive quantity, and the only one that you know is L2. If you could have here modulus helicity, well, there is no such thing. I mean, in principle, if you would have here, that'd be great. But we don't know how to do stuff like that. Okay? So here, circulation. Oh, beautiful. Sum of the absolute values of circulation of well-chosen loops. Okay? But you don't have something like that. So all you have is energy that is guaranteed to be okay. And you need this kind of continuity because this will guarantee that in the limit, your fluxes that you compute, the nonlinearity that you compute, is going to be in the limit, the nonlinearity that you want, namely u dot grad u, for instance. So you can think of this as being the approximate solution, and this is a deeper approximate, okay? So, or the quote-unquote exact solution, okay? And you want to know, it's essentially a convergence statement in a weak norm. but you don't want a convergence in which the constant here depends on the approximation or depends on the solution. Such inequalities are trivially true if you are allowed here to put derivatives of u. They're trivially true. And though usually in numerical analysis they are done all the time. This is how you prove that as long as the solution is smooth, my numerical method converges. Exactly like this. You put, I take the difference, I compute the difference, and as long as my good solution, 15th derivative is bounded, everything is good, okay? Here is the same thing except that the quantity that you put here is really the one that you know at the end is not going to blow up. Okay, that's all.
Mark?
Yeah, can I follow up with a very naive question? How would the Fourier transform of a weak solution of Euler equation with finite dissipation look?
So
How would it look if you look at the spectrum?
but my friend, I have the space right here in front of you.
Sorry, is this the same?
It's exactly this, right? So you're looking at this quantity. This quantity is L3, not L2, but okay, so modulo the fact that this is a cube of this. This quantity is essentially a constant for the dissipation to be non-zero.
So it would decay like k to the minus.
Well, this is minus a third, right? This is but it's L3. Yeah. I mean, I'm not telling you something new. This is Onsager conjecture. Okay? Actually, I'm telling you something new, namely that there are functions for which indeed this does not decay, and if you compute the fluxes, is non-zero. So the nonlinear term there indeed doesn't cancel.